Your phone unlocks the instant it sees your face. Your inbox quietly trashes the spam. A car reads the road. It feels like there's a mind in there, doing something almost human. There isn't. Strip away the mystique, and a neural network is doing something almost embarrassingly plain. It's drawing a curve through a cloud of dots. Here's the whole idea. The dots are examples it has seen. The curve follows them, so for a brand new input, it just reads a sensible answer straight off the curve. No understanding, no reasoning. Just fitting a flexible curve to examples, then reading off that curve. The entire field is variations on this one move. And the curve is built from one tiny operation, repeated: multiply, add, bend. Multiply, add, bend. Stack enough of those, and you can trace any shape at all. So let's build a neural network from nothing, one neuron at a time, until the word AI turns completely transparent. Start with a single neuron making one tiny decision: should you take an umbrella? It looks at a couple of facts about the sky. 2 inputs today. How gray the clouds are, call it 9/10. And how humid it feels, say 2/10. Just the facts, as numbers. The neuron decides how much each fact matters by giving it a weight. Heavy clouds should count for a lot, a big weight. Humidity less, a smaller one. Then it does the only arithmetic it knows. Multiply each input by its weight, add them together, plus a baseline number called the bias. Here it lands at 0.45. Finally, the bend. A positive total passes straight through, lean toward umbrella. A negative total gets flattened to 0, leave it home. That kink is the neuron's one spark of nonlinearity. Multiply, add, bend, a few facts in, one decision out. That is a whole neuron. Everything else is just this, repeated. Why does the bend matter so much? Watch without it. Here's real data. Crop yield against how much water you give, and we fit it with a straight line. Too little water and the crop withers, too much and it drowns. The truth humps in the middle, and a straight line simply can't bend to follow it. Look at the gaps. And stacking straight lines doesn't rescue you. Add a line to a line, you still get a line. Without a bend, a million neurons still draw one straight line. The fix is the kink. The simplest bend just says, keep the positives, flatten the negatives to 0, a flat stretch and a ramp, meeting at one corner. One kink doesn't sound like much. But give the network a few of them, and that crop curve suddenly comes within reach. Here's the move that makes everything work. Each neuron contributes just one bent line. On their own, they're crude and blocky. But line them up and add them together, and the kinks start to combine, the angular approximation creeping closer to the real shape. With enough bent pieces, the sum hugs the crop curve almost perfectly, peak, tails and all. Crude bends become a smooth fit. And this isn't special to crops. Mathematicians proved it. With enough neurons, this multiplied bend machine can approximate any continuous curve you like. That's the real headline, and it's geometry, not magic. A pile of dead simple bent lines summed is a universal shapeshifter. Real networks stack these neurons in layers: an input layer, a few hidden layers, an output layer, with each layer's outputs feeding the next. Take a concrete job, reading a handwritten digit. The input is just pixels, a grid of brightness numbers, each between 0 and 1. Nothing but numbers. Those pixels flow through the layers, multiply, add, bend, again and again, and the output lights up 10 options, 0 through 9. This one says 7. And the hidden layers aren't a black box. The early ones learn to spot tiny edges, deeper ones glue edges into loops and strokes, the last ones assemble those into a whole digit. However many millions of neurons sit in between, the whole pipeline is still one big function: pixels in, a label out. Nobody ever wrote rules for what a 7 looks like. The function just has to be shaped so 7-ish pixels come out as 7. Which raises the real question: how do you shape it? At the very start, every weight is random. So the curve is nonsense. It ignores the dots completely, missing nearly every one. To improve, you first have to measure how wrong it is. For each dot, look at the gap between the curve and the real answer, that red distance. Square each gap, so a miss always counts as positive, and average them. That single number is the loss, the network's total wrongness. Averaged over thousands of examples, every crop plot, every labeled digit, the loss becomes one honest score for the entire network. And now the whole of learning collapses to one sentence. Find the weights that make that loss as small as possible. Picture every setting of the weights as a place on a vast landscape, where height is the loss. High ground is bad, big error. The valleys are where you want to be. Learning is just rolling downhill. Drop a ball on that landscape and let it roll toward lower ground, towards smaller and smaller error. At each step you ask a purely local question: which way is downhill from right here? Then take one small step that way, and ask again. Calculus gives that downhill direction exactly, it's the negative of the gradient. The update is a single line, nudge each weight a little against its slope. The size of that nudge is the learning rate. Too big, and the ball leaps clean over the valley. Too small, and it crawls for an age. Get it right, and the loss tumbles. It isn't flawless. The landscape has dips that aren't the deepest, local minima, and the ball can settle in one. In practice, a little randomness and momentum usually shake it loose. Repeat that nudge millions of times, and the random curve from before slides into place, right through the dots. That, and nothing more, is training. There's one catch. A big network has millions of weights, and you need the downhill slope for every single one. Working them out one at a time would take longer than forever. The shortcut is backpropagation, and the idea is really just assigning blame. The output came out too high, so which weights pushed it up, and by how much? You start at the error and walk backward through the layers, handing each neuron its fair share of the blame, using the chain rule from calculus. One backward sweep through the network hands you every slope at once, reusing the shared work, instead of redoing the calculus a million times over. So backpropagation isn't a brain or intuition. It's careful bookkeeping for one enormous derivative. No magic, just the chain rule at scale. Step back, and the mystery dissolves. A neural network isn't reasoning. It's fitting a flexible curve to the examples it was shown, then reading answers off that curve. Which tells you exactly where it shines and where it shatters. Inside the cloud of data it has actually seen, it interpolates beautifully. But push it outside that cloud, and it's just extending a curve into the dark. Ask our crop model about 10 times more water than any experiment, and it predicts confident nonsense. Same with the digit reader. Show a network trained only on cats and dogs a picture of a car, and it won't say "I'm not sure." It'll shout "dog," because nobody taught it doubt. Worse, you can fool it on purpose. Nudge a few pixels, changes far too faint for your eye to catch, and a confident panda flips to a confident gibbon. It reads patterns, not meaning. The power is real, but it's geometry and calculus at colossal scale, a curve fit to the past, not a mind that understands the present. So the next time something is sold to you as AI, picture the dots and the curve. It learned a function from examples. It wasn't handed rules by a programmer. And the recipe is small enough to hold in your head: multiply, add, bend, repeat, then roll the whole thing downhill until the curve fits. Behind every dazzling model is that same humble loop. Not a ghost in the machine, just arithmetic, bent into shape, and rolled downhill.